Alright, another DraftScience video presentation. Just almost a production. It's almost produced now. Yeah, almost. Anyway, gravity. Probably push, 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 push. Push, pull. There's no examples of pull. Just can't find one in our reality. Every time I'm pulling on something, like say I held this chalk and I held it at this end, I pulled on both ends. I'm really pushing on the substance of the chalk. I'm actually pushing it that way. That's how it knows the experience. If you ask the chalk what's happening when I'm doing this, it says somebody's pushing me that way and somebody's pushing me that way. That's what it's going to feel, because that's what's happening on its surface. I'm pushing on the bits in that direction, and I'm pushing on the bits in that direction. It's always a push. So there's really no pull. And that should be like simple, like this whole idea of the two different things, matter and force, the stuff moving the speed of light, the some things that are getting pushed at some other speed. The fact that it's speed of force, not speed of light. You can just go through these things, and it's just disappointing that physics never really ties up these knots and never really explains momentum or kinetics. In the sense that you can imagine it happening different ways. Things banging into each other and bouncing off, and this thing stopping, and that's what we see because we're seeing force being transferred. We're not seeing the real universe where the force is actually acting, and you can't just transfer a force. There is actual forces moving. And so we think the big universe is the little universe, and the big universe has force collected in objects, and then the force is transferred from object to object. But at the elemental level, that's not what's happening. Force actually has to hit matter and interact with it. Can't give it something and then leave with less in its pockets, so to speak, in any obvious sense. And I've sort of given the simple fix, where the matter bit, the electrons, the protons, have to actually be hit by the force. The force has to stick, essentially, to move it. It doesn't move if it doesn't keep pushing it, in the sense that the little bit just hits it, and like Sisyphus, it has to push the boulder. And then another action happens, and that releases it. So until another action happens, this little thing pushes it. And on the universal scale, that's how this energy thing's happening. Every billion trillionth of a second, a little bit pushes something in a direction, then something else hits it, that one releases, that one pushes it somewhere else, and then another bit hits it and pushes it somewhere else, and that's what's really happening. And the matter thing never moves the speed of light, so it's always kind of absorbing some energy of the force, in the sense that the force, when it's moving an object, isn't moving as fast as it should be. So it should be over here, right? And it's only here because it's moving matter. So it's lost a little bit of its energy to push the matter. Simple, just insanely simple explanation. It completely explains why more energy goes into an object and less energy comes out. And that's gravity. That's what's causing gravity. More goes in, less comes out. That means everything's creating a little bit of a deficit, and that little bit of a deficit, when you put a whole bunch of material things together, adds up to a lot of a deficit, or enough to make you fall in gravity. So anyway, I'm going to keep talking about this stuff because it so fits, it's so complete, it answers all the questions, it fixes it all, and, I'm getting nothing back. No comments, nothing. Nothing, zero. It's just incredibly, nothing. Not even anything close to an explanation of how it can't be that way. And not even anything like, wow, that's so simple. Surprising that smart people could be so stupid not to even consider such an explanation. Seems like somebody should have thought of it first, and first shouldn't be 2020. First should have been a long time ago. And that's sort of the history, though. There is a video I'll play later, maybe, on Lesage gravity. And they can't even, again, they don't even cite the guy who actually first proposed it, this guy Fadio. But whatever. The fact is, it was thought of before me. And the irony is, well, not really an irony, is I didn't know Fadio or Lesage existed, and I thought of it. So, I mean, it should have been somebody else. There should be more than just three of us. Yeah. There should have been more. But anyway, I fixed all its flaws. They weren't that hard to fix with modern physics. Modern physics sort of allows you to fix it because you can understand that there are electrons and protons, and there is this distinction between this little stuff moving the speed of light, the forces, and the material bits. And, you know, in 1600s, that wasn't so easy to understand. It wasn't so obvious. Alright, I think this is the right thing to click. That appears to have worked. So let's see how this goes. Technology and such, still trying to get used to it. So it'll take a little bit of time for me to become proficient at this. So we'll hit the play button. And
Years from the surface of the Earth, a rapidly spinning neutron star called the Black Widow pulsar blasts its companion brown dwarf star with radiation as the two orbit each other every 9 hours. Standing on our own planet.
so that's their deduction based on little tiny things, right? So again, we understand that physics is limited in terms of the evidence of a lot of this stuff, and so they have to take tiny amounts of dots, right? We're connecting dots and try to see whether it's Goofy or Donald Duck or Mickey Mouse, right? The picture. And they keep taking, we have very few dots to work with. And, you know, what clearly happens is everybody likes Mickey Mouse, and so they all try to make it turn into Mickey Mouse, and it's not Mickey Mouse. Yeah.
You might think you're just an observer of this violent ballet, but in fact, both stars are pulling you towards them.
So again, pull, 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 which is an impossible elemental force. There's no way to make an elemental pull unless you believe in fairies and magic. It just makes it, you know, move towards. I mean, it just, there's no elemental pull. There is an elemental push, and it's called collision. So we know that elemental push is really easy, just have a crash. Where elemental pull, not so easy. So right there, physics was given a huge, giant clue. I mean, that's a dot that should be a big, fat dot on the piece of paper. Push, elemental, pull, no chance. So every time they look at a movement, they should be saying what's pushing it first. Okay, and then figure out where there's a missing push. Okay, so two things should be pushing it, and only one of them's pushing it. And then they could say, I understand, push it goes that way. Because one of the pushers is gone. One of them's missing. Yeah, that's the way they should be looking at it. That's the beginning. That's where you start. And obviously that's not where they started. They started somewhere in the middle and then decided push fits with their fantasies better, pull, than push. And they never even reconsidered, well, maybe we got that all wrong. I should be able to do this.
And you're pulling back, connected across trillions of kilometers by gravity.
So I thought it was funny just the way they illustrated this. I just thought, what the hell? I mean, this is what their theory really is. It's just a bunch of little fairy sparkly thing, fairy godmother. It's all full of little pixie glitter and crap. You know, there's no theory here. There's no physics or mechanics. It's just this little wooey image of the simplest, most abundant force there is. I mean, the one that's the most obvious in our existence. And they're just, let's do it this way. We'll conceptualize it as sparkly, magical unicorn farts.
The attractive force between two objects with mass. Any two objects with mass.
So again, when they say this, any two, they sit there and go from planets to big things, and what they should be saying is electron, proton. They should at least say atom, Okay, one atom will do exactly the same thing in an orbit that the planet does, right? I could throw one piece of chalk into space right close to the Earth, and it'll do exactly the same thing orbiting wise. It'll have the same velocity, move the same way, fall proportional to its mass. It'll do exactly the same thing, and I could take the chalk and turn it into an atom, and then I could take the electron and proton and put them in space, and they'll do exactly the same thing. So we know this gravity thing comes in the form of an atomic bit. It's a nuclear force, okay? The nuclear bits are what are affected by gravity. The gravity exists, and it doesn't affect just atoms or just molecules. I mean, it doesn't change. It always is related to how much of that atomic stuff you have, right? I mean, how they detect mass, well, it's the same thing as your atomic number. I mean, it's the same thing as your physical atomic mass, and your atomic mass is electrons and protons. So obviously there's a correlation between electrons and protons and what's going to happen to you gravitationally. So why not draw it that way? Make it understood where it starts, and it starts on the very smallest things are affected by gravity. They're the bits. The mass is the atomic number.
Which means that every object in the universe attracts every other object. Every star.
So the word attract, when, technically they're really not getting attracted, they're getting pushed into each other. So this isn't like a marriage made in that kind of way. It's made how everything else happens. We're more pushed into doing what we do than we are pulled into doing what we do, right? We're running from the bad day more than we're going towards the good day, kind of thing. We want the good, and we get to the good by avoiding the bad. I mean, this is a theme that exists in the universe. And again, it's just so you can add a little philosophical element and understand that this rhetoric, these words, are very destructive to physics. Physics should have a moratorium on naughty words. Okay, spontaneous, no. Random, no. There's lots of bad verbiage in physics, and it's pretty obvious, and they should do something to fix it.
Black hole, human being, smartphone, and atom are all constantly...
There we go. So atom, they should have gone to one step further, just made it clear that this obviously has something to do with material bits, the bits that make up matter. And what do the bits that make up matter do? They move from one position to another position. So it should be understood that maybe in the process of moving from one position to another position, they're creating gravity.
Pulling on each other.
So pull. No. Wrong.
So why don't we feel pulled in billions of different directions? 2 reasons: mass and distance.
Well, those are good reasons, but better understood as rays. It's all or nothing. Okay, you either do get hit by the bullet or you don't. So if I was shooting randomly, right, that there's a very unlikely, it turns out, there's lots of space a bullet will come back down to, and then the Earth, although there are a lot of people on it, there's like a square mile for every person of empty space. I mean, space that's not another brain. So the odds of you shooting bullets up and having them land in a brain, aren't very good. Okay, and it's all or nothing, right? You either get hit by a bullet or you don't get hit by a bullet. So this is another example where you can sort of understand that as you go further and further away from some loony shooting bullets, that you're going to be less and less likely to get hit by a bullet. That the ratio of bullets to empty space gets higher and higher and higher. And that there could theoretically be a distance I could go where, it might take 10,000 years for one of your bullets to hit me. 10,000 years. So I'm obviously not in your gravity if it takes 10,000 years for me to see a difference, to me see a bullet that actually hits me. So you can theoretically outdistance the force in the sense that your neighbor might get a bullet in his head, but you won't. It won't be, it's personal. And that's just the way it is. It has to happen to the individual, and it's either, like I said, you either get a full clump a quanta of gravity, or you get nothing. And the gravity is just the absence of a bullet in this case, the irony is.
The original equation describing the gravitational force between two objects.
Right, now this was always another thing where they should just say, well, wait a minute, what are we really saying? We're not saying that you have to have the two objects to have gravity. Right? We all kind of knew that there's this, gravity existed before I fall into it. I don't need to show up. The Earth is sitting there going around the sun. You can kind of understand, the gravity's already there. I'm not going to be making it by showing up. So we know this equation is somewhat flawed in that sense that it's saying, what's the total effect of both of your gravities? It's basically saying, let's add up both of your gravities, because both of them will matter. And for both of them to work, both of them you have to be there with the other thing having the gravity. So the equation needs both of you in it for you to calculate the actual force that you're creating, the deficit in the gravity, and the deficit the other thing's creating in the, what goes in versus what comes out. So we're all sitting here getting hit by stuff, and there's a little less stuff coming out. And the more mass you have, the bigger that ratio of how much stuff is being not coming out, is being diminished. And so it's proportional to your mass. And so obviously you have to have both in there for you to have an equation worth solving. But the truth is that each individual object is making gravity all by itself. You don't need the other m to know what's the gravity of the thing, itself, all by itself. And it's never stated, ever, as far as I know, ever stated that way.
Was written by Isaac Newton in 1687.
Right, so we should have improved on it a little bit, but instead they threw it in the garbage and decided to use this gamma frickin', stupid Einstein bent space time factor thingy. They decided to try to break it, but it has the elements you can't break. The inverse square law, for example, the r squared in the bottom of the equation is rock solid. And again, the relationship to how much energy you can absorb is based on how many atoms you have, and how many atoms you have tells you how many electrons and protons you have. So it's how many electrons and protons you have, and how much they move is going to be dictated by the universe itself, and so they all move about the same amount. So the more you have, the more movement you have. The movement is absorbing a little bit of energy. There you go, gravity solved. Simple, simple, simple. Newton would he'd be like, oh, you got it. That's such the right answer. I had to keep saying things like, well, I tell you what it does, but I can't tell you how it does it. Oh, well, now I can tell them how it happens. That's how it happens. Energy is absorbed by mass. When mass moves, it consumes a little bit of energy, because that perfectly makes sense. It can't go somewhere unless it absorbed energy somewhere. And what did it absorb? It absorbed the speed of the force while it was moving the object. The object loses speed just while it's moving it. It doesn't lose it permanently. It just loses it for the period it's moving the object. Sisyphus only has to work when he's pushing the boulder. When he goes to push the boulder and it's not there anymore, well, now he's back to normal. He's not being slowed down or burdened. I mean, it's so simple. And it's just, I'm sitting here saying it's so simple. I'm sitting here saying, I got the answer. I solved the problem. It's completely solved. I can tell you exactly what the image is. And once you know what the image is, you can fill in all the dots, and all the dots fit, and it all fits together. And you're just sitting there, who cares? No. You're all going to look so bad in hindsight. Like, how did you not realize this was the right answer? I mean, it was so obviously the right answer.
Scientists' understanding of gravity has evolved since then, but Newton's law of universal gravitation is still a good...
Evolved is a stupid word to use, because it didn't really evolve. It did some perverse thing where it jumped to fairy godmother space. It jumped to some vacuous, silly, non-physical explanation that was just a god of the gaps poof. The poofy space is vacuum cleaner. And in 3 dimensions, it's vacuum cleaner. Let's just understand the spent space thing doesn't mean anything. It's an analogy, a metaphor. It has nothing to do with the real universe, because the real universe isn't a tablecloth you can bend. All right, the real universe doesn't work that way. The real universe has to do it in 3 dimensions. So it has to create a vacuum cleaner. So that was the answer. Einstein showed him, said, vacuum cleaner. I guess vacuum cleaner. Everything's a vacuum cleaner. And you know, that somehow makes more sense to you than a bunch of energy in the universe going in all directions and that creating exactly the same scenario where everything's pushed into each other. And you went for vacuum cleaner. Well, you went for it because they didn't say vacuum cleaner, right? So if they would have said vacuum cleaner, you would have said, oh, bullshit. Vacuum cleaner with no outlet? You just suck the air in, but you don't have to blow it out anywhere? You would have said, oh, bullshit. But so they hid it by just saying a bunch of jargon and goop, and so you fell for it. Sadly. You're all so doopy. You're so borged. It's just amazing. I just don't know, how did I end up on this planet of Borgites?
Approximation in most situations. It goes like this. The gravitational force between two objects.
La 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 la. I mean, that was just such a piece of la la. Oh, the gravitational, the magical. Zzz. You know, it's like they're the emperor and they can shoot electricity out of their fingers. Zzz, I'm gonna zap you, Darth Vader. I mean, it's just such a little fantasy.
Objects is equal to the mass of one times the mass of the other, multiplied by a very small number called the gravitational constant.
Completely irrelevant, right? You're only multiplying it times the number of pieces of chalk. You have to put it into. It's like if you had an economy and there was a certain amount of sheep equaled the certain amount of pigs, in terms of value. You have to have some sort of constant to be able to equate between these different ways of measuring. So the only reason the G thing exists is to say, okay, I'm going to put this into some sort of confined units of energy, and that's all it's for. It's just to give you units. I mean, obviously there's a constant, and the constant is electrons move a certain amount, and that takes a certain amount of time, and at the speed of light, a quanta of light, a little clump of light, will lose a certain amount of energy moving an electron.
And divided by the distance between them squared. If you doubled the mass of one of the objects, the force between them would double too. If the distance between them doubled, the force would be 1/4 as strong.
Yes, well, that's the one he should have emphasized, because that's just the radiation argument. All you're really saying is every point source, every spherical point source that radiates energy evenly creates the inverse square law. So again, this hand, all right, half the distance, 4 times bigger. It's 4 times bigger here than it was here. Okay, so there's this inverse square thing is in a lot of places, and it just has to do with the rule, okay, that as the stuff spreads out, it spreads in a square. Okay, it spreads both this way and this way, which means it gets 4 times less dense with distance.
The gravitational force between
you and
the Earth pulls you towards its center. A force
so you got pushed. Okay, the simple truth is, again, anywhere there's matter, there's little jiggling electrons and little jiggling protons, and as they're jiggling, they're using up energy. They're forcing Sisyphus to do work. And so Sisyphus can't go to the grocery store. Sisyphus can't do all this other stuff because he's got to move electrons and protons. And so you end up going in the direction where there's less people throwing stuff at you. Sisyphus is busy. He can't push you back the other way. So the Sisyphus behind you push you forward. That's all it is. It's so frickin' simple.
Experience as your weight. Let's say this force is about 800 newtons when you're standing at sea level. If you traveled to the Dead Sea, the force would increase by a tiny fraction of a percent. And if you climbed to the top of Mount Everest, the force would decrease but again, by a minuscule amount.
Well, it's not that minuscule. I mean, it's like 1/4%. You know, it's something. But anyway, yeah, it's a small amount because it's a small amount of total electrons and protons. Okay, so you just went from a billion to a billion 400. You know, it's just not enough of a change where you're going to be able to measure the difference. You're not going to be able to tell the difference between the thickness of a book that has a billion spots in it and a billion 400. They're going to look the same to you. So you don't, but it's not an insignificant difference.
Traveling higher would make a bigger dent in gravity's influence, but you won't escape it. Gravity is generated by very...
You won't escape it unless you understand that time, you know, there's a certain amount of time limit, you could argue. You won't escape it if time is infinite. But if time isn't infinite, you can certainly escape it. Like if you live 100 years, you could go somewhere in space where in those 100 years you'll never be affected by the gravity of half the stars in the sky. It'll never affect you. You could go to some place far enough away. And truth is, it never affects you in those 100 years. So, but yes, if you live 200 years, then there's a higher percentage. If you live 500 years, eventually the bullet's going to hit you.
Variations in the curvature of space-time, the 3 dimensions of space plus time, which bend around any object.
So again, the phony description, there's no bending around, there's no such thing in 3 dimensions, there's no three-dimensional bending, it just doesn't make any sense at all. It's obviously a vacuum cleaner, and they just don't say vacuum cleaner, because then you would say, oh, too silly.
It has mass. Gravity from Earth reaches the International Space Station 400 kilometers above the Earth.
Right, 400 miles, it's nothing, right? I mean, it's just nothing. I mean, it's driving from Florida to, like, Virginia. I mean, it's nothing. So, obviously, it's not very far. So, obviously, it doesn't make that big a difference. And, obviously, the reason why they're weightless in space is just because they are still falling. They're just have a good enough velocity that you don't see them falling.
With almost its original intensity. If the space station was
there it is again. So we know the gravity is the same place at 400, then at 600 and 900. You just keep going out kilometer-wise and just keep showing how the gravity is decreasing. Okay, and that it's decreasing by that incredibly strong R squared factor, which means it's getting weaker, 4 times faster than you're getting away from it.
On top of a giant column, you'd still experience 90% of the gravitational force there that you do on the ground.
And that sort of tells you that the Earth is 4,000 miles in diameter in a way, right? Yeah, kind of.
Let's just experience weightlessness because the space station is constantly falling towards Earth. Fortunately, it's orbiting the planet fast enough that it never hits the...
See, it'd just be good if they just showed that in the simple sense, and that the space station's traveling a straight path with its velocity, but it's getting hit by this absence of force. So, because there's less force hitting it this way and more force hitting it this way, because the Earth has absorbed that energy, that its path gets bent and bent and bent. But it keeps going straight. It's 2 forces added, 2 straight line forces. They should draw it as 2 straight line forces combining. There is no circular orbit. There's 2 straight line vectors that decide the next position. There's no curved path, especially for the force.
Ground. By the time you made it to the surface of the moon, around 400,000 kilometers away, Earth's gravitational pull would be less than 0.03% of what you feel on Earth.
So I guess that's 10,000 times the diameter? No, it's more than that. But it's not as far as you think, right? I mean, it's a long trip, but it's only like, you could add up like 100 trips around the Earth to the moon, something like that. I don't know. The circumference? I don't know.
The only gravity you'd be aware of would be the moon's, which is about 1/6 as strong as the Earth's. Travel farther still, and Earth's gravitational pull on you will continue to decrease, but never drop to 0.
See, that's the tricky part. Like I said, it does sort of drop to 0 for very long periods of time. where nothing happens. And you can sort of see that with time-lapse photographs of the universe. They have to take the photographs over a period of time because not enough photons are coming down. So at any one instance, there's no, all those images don't exist for any one moment of time. And so you have to wait a long time to collect enough photons, So it's the same thing. So you can get pretty far away where you're not collecting too much. It takes a long time to collect anything.
Even safely tethered to the Earth, we're subject to the faint tug of distant celestial bodies and nearby earthly ones. The sun exerts a force of about half a Newton on you.
I mean, it's very, still.
If you're a few meters away from a smartphone, you'll experience a mutual force of a few piconewtons. That's about the same as the gravitational pull between you and the Andromeda Galaxy.
So it's just a matter, again, in distance and mass, so we understand how weak this change in the field is. But again, when you just think of how many electrons and protons there are in the Earth, you can get the idea that, okay, this is a tiny amount being created by each electron moving or each proton moving. It's a tiny change in the overall energy of the universe. But obviously, when you condense a bunch of mass, then you have a lot of stuff jiggling, a lot of consumption.
Which is 2.5 million light years away, but about 1 trillion times as massive as the sun. But when it comes to escaping gravity, there's a loophole. If all the mass around us is pulling on us all the time, how would Earth's gravity...
So again, pulling on us all the time, that just can't happen. It has to push on you all the time. So that's see how the analogy fails in the sense that it's thinking that this pulling thing is happening as an interactive mechanism, and it's really not. It's just where is there force and where isn't there pressure. And it just has to do with the pressure that we experience is dependent on what all those other objects have done to the space as it's heading for us. I mean, when you put something between you and the rest of the universe, it's doing something. And the fact is it's absorbed energy. More of it hit than got to you. And the same amount of that is what you're going to get affected by. What am I supposed to hit? Oh, spacebar
would
works.
Change if you tunnel deep below the surface, assuming you could do so without being cooked or crushed.
And why would you be cooked or crushed? Well, part of it is because the matter is jiggling. Okay, so that's heat, right? You're absorbing force by moving matter. So that is, in a sense, is going to convert into heat, some measure of heat. So you really can't escape the temperature of the universe. As soon as anything's hitting you, you have a temperature. So this idea that they could ever find an absolute zero is absolute nonsense. But anyway, beyond that, clearly the gravity gets converted into pressure of atoms actually moving. The atoms are being moved by the gravity, and they can't move in one direction because something else is moving in the opposite direction, just like we are not falling through the surface. And that agitation creates jiggles in entire material objects, which creates heat. So the whole reason why the Earth is hot is because of gravity. And the pressure is also a consequence of gravity. Gravity is pushing on the outside. The atoms are banging into each other, but some are still going that way, the wrong way. And so there's lots of collisions taking place. And as you go deeper and deeper, your converted gravity from the little minuscule raindrops to the collective pressure, and that pressure can come from any direction. The chemical pressure moves in through the sides because there's less pressure going sideways than there is up. And so the whole gravity is still the physical pressure that the rocks are under and that the dirt is under and all those things, the things moving them, is still gravity that's doing it. It's just been converted into movement of whole atoms and movements of whole rocks. The movement has been converted into movement in one direction.
If you hollowed out the center of a perfectly spherical Earth, which it isn't, but let's just say it were, you'd experience an identical pull from all sides, and you'd be suspended weightless.
Right, but you would have to overcome, to do that, all of the force of gravity for the entire mass of the planet Earth to make your vessel. Your pressure would be the mass of the entire Earth's worth of gravity in all these directions. So the whole thickness of the Earth, the gravity that thickness would create, that many atoms, you have to compound that force, with you have to make some sort of, bubble, and the bubble will have to overcome a huge amount of pressure. So you're really just saying, okay, I've blocked the gravity by blocking its consequence, which is the pressure of the magma or whatever I'm in. If it was made out of solid rock, it'd be all this rock pushing, at 1,000,000 pounds per square inch or something, some preposterous amount of pressure. So they don't even say that.
Only encountering the tiny pulls from other celestial bodies. So you could escape the Earth's gravity in such a thought experiment, but only by heading straight into it.
See, the other argument would be is you didn't escape it. You just have both gravities affecting you. You essentially have a moon on one side of you and a moon on the other side of you, both creating gravity, and you're just neutralized. So wherever you move, you're just neutralizing two equal forces. And because you made a spherical opening, it's the inverse square law kind of thing again, the radius thing again. So as you move from one side of the circle to the other side of the circle, even though you're exposed to more gravity from one side than from the other side, the side you're closer to is stronger because you're closer to it, and the side you can see more of, you're further away from. And so that becomes the balancing factor.
Keep flexing your physics muscles with this TED-Ed series in which two CERN scientists simplify space-time in 3 short videos.
Yeah, you think that's going to happen? I don't think so. No chance. Blah, 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 blah. TED-Ed, whatever that is. Anyway, alright, so we'll move on to... maybe I'll just draw some of what I just said. So we'll move on to this and see how this works. Yeah, cool. Alright. So I don't know if I'll need to get into colored things again, but I probably should do a charge video and just make it clear so it's understandable. But let's see how this works. So I could pause, and that would probably be a good idea. I could pause my way out of the clunkiness of that introduction. And I guess I should try to see what my size is here, and where can I go up here? Right about there. So I have to draw it in that box. Okay. It's smaller than I thought it would be. All right. Anyway, so so the idea is that every atom, okay, as it's moving, as it's sitting here, right, every electron and every proton is interacting with the force in such a way is that, the electron doesn't move unless something forces it. So it's like a balloon in a bunch of BBs, or however you want to describe it. So let's just say a bunch of BBs in a box, and I have a little hollow piece of plastic. And the only way the hollow piece of plastic gets momentum is, you understand, a BB has to hit it. Now, those reactions are going to be purely reflective. So you know that you're really transferring the force, and the BB leaves slower than it got there, and so it's a little bit different. And so what I'm saying is the difference to understand is the explanation that makes it work even better. Now it'll work, right? If I did this, if I took 2 plastic balls and I put them in a box full of BBs, the two will move right into each other. It's called mock gravity, and it works. If we could build that box easy enough, and the BBs didn't lose energy, the fact is the 2 objects will move right into each other, just like gravity. So it works as a theory. It's a substantial explanation, not an unsubstantial one. They try to make it sound like it's easily debunked, but it really isn't. So all I'm suggesting the difference is that the force itself, these aren't force carriers, these aren't 2 massive objects hitting each other, these aren't, when force interacts with matter, let's just say an electron, it actually has to maintain it has to keep it moving. You can't just hit it and the force stops and this thing goes. You can kind of understand that that wouldn't be conservational. Okay, you'd be creating energy in the universe. This thing would be going somewhere, and if you have this thing reflect right off that instant, well, now you have more energy in the universe, but you have this energy is conserved, and now you've added this new motion into the universe. So you know you can't add energy, right? So there's got to be some other answer. And I would say the simple answer is that the little bit, you could just say these balloons are sticky. But they're sticky in a special way. You know, like I said, this thing has to hit it, and it moves it, right? So it goes, this electron goes from here to here, but it does so less than the speed of light. It moves from position 1 to position 2, less than the speed of light. That means the force that was going the speed of light, it traveled from here to here eventually, but it did it at less than the speed of light. If you calculate its total path and how long it took, it's moving less than the speed of light because it spent some time moving the matter. So Sisyphus walks slower when he's pushing rocks. And then the key to this being released is going to essentially be another bit hits from the other side, and then it becomes quite kinetic. Okay, this bit that was over here is momentum. It crashes into that momentum, so this one just reflects, and this one that was pushing, it reflects. So now you've conserved the energy. You've stopped this from moving. So this is completely conservational. And you've given this back to the universe, right? You've given a piece of force back to the universe. You have something going that way, which essentially was this piece going that way. It's still going that way. This bit that was this bit now, right, is essentially going this way. So the outcome is exactly what you had in terms of forces. You had a force going this way, and now you have a force going this way. You're going to have a force leaving this way, and you're going to have a force leaving this way. So that will be equal, and this will be stationary. So that solves the problem. So what happens is you you hit something, it moves. It hits something else that stops it from moving. Then something new will hit it, okay, and stick, and it'll move. But when something else hits it, that will reflect, and the other thing will reflect, and it'll stop again. And the idea what keeps electrons moving are things like gamma rays, right? Where you can have a bunch of force piled up on each other. You could call them waves if you want to. Oh, rather the image, right? Yeah. All right, I'll have to do something to fix that in the future. I suppose I could move back a little. Yeah. Oh, that's a little better, but still, okay, you get it. Okay, so I got it over here. Now all I have to do is move it over here. So the idea would be is an electron could be hit by a gamma ray, which is a bunch of energy very close together, very high frequency. So you can understand that if a gamma ray got behind an electron, well, the electron would move. It's moving into force, so it's going to hit more force sooner, and then it would stop, right? It hits a little force bit, stops. And then, but it's got this whole chain here, so it reflects one piece of the chain comes off. And then it hits another bit, and then one piece comes off and reflects, and then it hits another bit. But you can see that this will cause it to move very fast because every time it hits something, it's already got a replacement. It's already got a new bit to keep it going this way. So it's got this frequency, it's going to be higher than the frequency it's plowing into, and therefore it will go pretty fast. But for a confined amount of distance, and that's what we see in electrons as they go. You can shoot them very fast, but they don't go very far. Okay, and they run out of fuel, and the fuel is this. The fuel is the ray length of the gamma ray, or the X-ray. That's almost on the board. So it's a little bit of glare there. I'll have to see if I can fix that in the future. How dark to make it. I don't really want to make it darker. You know, this is all little stuff. I haven't completely got all the bugs out of this yet. Working on it. Yeah, well, that'll have to do. Sort of works. You know, mostly, kind of, partially. See, I could have drawn higher, and that's what I should have done from the start. All right, so, you know, as stated, So all you're doing when electrons and protons are sitting inside the Earth, they're obviously getting hit by little bits of force. They're being held in atoms, and the atom has a bunch of force hitting them. And so you can sort of understand that if I'm correct, that the force moves it and then steals a little bit because it moves it, and then it stops moving, and then it moves back this way, and then it moves this way, and then it moves this way, and it moves this way. It moves in all directions. And what's happening was each time the electron jiggles, it consumes a little bit of energy from the force. The forces go from A to B, and they don't quite, you can either look at it two ways. They either don't quite get there because they're behind, because it's wasted some time doing that, or you can understand that they travel the distance in a longer time. And either way of understanding, A is over here. Yeah. Can't see. Oh, there he is. Okay, you can almost see A now. Yeah, I guess I could just do it at an angle. Sorry, first try. I could have practiced, but it takes time, and who's got all this time? I don't. So anyway, you can sort of understand it's always consuming the energy in all directions, and that's why the gravity is in all directions. That's why it looks like a vacuum cleaner, technically, right? Is because it consumes a little bit of energy out of the universe. So again, as stated, the object is basically at a thermal not equilibrium. The universe sends in so much stuff. It should be getting to its point B's at a certain speed, at the speed of light, and it's not going to get there at that speed. And so that's a little bit of momentum you've taken out. So the stuff comes in and a little less comes out. Okay? And that's what's causing gravity. Such a simple explanation. So simple. And we're done with all this woo, entanglement woo, bent space woo, time dilation woo. We don't need any of that crap to explain the physics of the universe. And then it's really physics, right? It's not this wooey crap. All right, let's jump ahead to over here. All right, so this is Massage Gravity video, and I'll play some of this, if I can remember where it is. It's still in the YouTube frame, so we'll have an ad, no doubt.
The most successful attempt to provide.
I can't hear it. So.
Came from the Swiss-born scientist Lesage. He was born in.
All right, so I have to turn the actual volume up. So that's the downside of using these different things, mechanisms. Some of them. Where the hell's the little? Oh, it's this stupid music thing. What a stupid icon. All right, should be more than enough.
1724 in Geneva.
Well, that didn't work at all. How come it gave me this much simpler one before? So the microphone's all the way up. Oh, shit. This is not what I'm looking for. It's not working. Alright, sorry. Technical difficulty.
He was an atomist and wanted to explain all properties of matter in terms of collisions and conglomerations of atoms. He saw a way
This is crappy
to
audio.
use this to explain gravity itself.
It really shouldn't be crappy audio. There's really no reason for it to be crappy audio.
Lesage's theory is interesting for a number of reasons. Firstly, it is a prototype of a dynamical explanation of Newtonian gravity. Secondly, it actually...
this crap, Facebook, paper, it's just so obnoxious. Eek. All these fancy graphics, and to put that shit on top of it is just such... it just surprises me that they just don't say inside their head. If I have to tell somebody that crap, they're not going to understand a word I'm saying. They need me to, Facebook on them.
comes very close to accomplishing this. We will examine later modifications to this main theory in later videos, but for now it is important to understand that this theory is able to describe all of the effects of gravity we know today. The
point is this BB and checker example works. The fact is, it will create, the two things will move into each other, and they will move into each other by some gravitational constant, depending on how fast your BBs are moving. And the inverse square law will be obeyed if you could do it in 3 dimensions and all of that stuff. So it does create pressure model does create very good gravity. The downside is they say it has this side effect, which was drag. And the fact is, though, is drag is a real thing. And the fact is that big matter overcomes drag by creating little engines inside of it, little motors, you could call them, proportional motors that say the more pressure you put on me, the more pressure I can create to counter it.
Some side effects from this theory, which in the end were its main downfall. But as we will see in future videos, these downfalls may in fact be key pieces of evidence that we are able to explain with minor modifications to this theory.
Now, I'm sure they're not going to do that, because obviously if this was in any way rational, it would be something, but it's, so they're not going to do that. But we'll see what they're going to do.
The third point to know is that this theory has been around for a long time and attracted comments by leading physical thinkers over several successive generations.
And that's just more bullshit. It's attracted a bunch of negative comments, unfortunately. Obviously, some people thought it had some value, and some people thought it had no value, depending on whether they were devoted etherists or not. And that's about all it comes down to. And so Newton liked it. Again, well, let him do it, and then I'll point out how he's just being, it's not hard to find the truth, and so I don't know why he doesn't tell the truth.
So let's get to the crux of Lesage's theory of gravity.
It's really not Lesage's theory, so this is the whole problem. He was just an advocate, so he came later. He didn't invent the political party, so to speak. He was just a member of it. And what Lesage had done was he actually paid for, the rights to Fadio's papers after his death. And he didn't substantially change the theory. So it's basically a theory that Fadio invented, a French guy, and that guy actually corresponded with Newton. And so Newton did like the idea, but there's no specifics about when or how Newton changed his mind, or if he changed his mind. That history is a little bit unknown. But clearly there was a falling out of some kind between Fadio and Newton, but it might have just had to do with Fadio had some weird politics. He belonged to a cult and some different things, so who knows what the truth is there.
He imagined that the universe was filled with a sea of very small particles he called ultramundanes. The main properties of these particles are that they have a minute mass, enormous speed, and travel in...
So they didn't know what we know now, right? So we know now that would be called force. These would be little big pieces of force. It would be little broken photons, right? Photons you can't see but are still there. We know they exist. Cosmic background radiation style energy. So it's energy moving the speed of light. So we do know it has a speed. And again, the key ingredient is that speed is reduced to move matter. And when you reduce the speed, you reduce the momentum. So you actually did do an energy transfer, and through the energy transfer, there's less coming out of an object than went into the object, and that's gravity. So it's that simple. They were that close, but they just didn't know enough to be able to say. They couldn't build the model out of the world they knew, because the world they knew was rocks and snowballs, and they're just not good enough examples. We didn't have the example of bird flying, and I tie ropes to the bird, right? And the bird's still flying, but he's got to pull me, and then I let the bird go. And then some understanding that, yes, that if I do that to all the birds, that the birds are going to end up flying slower. There's going to be less birds interacting in the universe because I'm slowing down their function. I'm taking a little bit of their energy away from them. I guess they have the capacity to analogize it, but they just couldn't turn it into something. They just didn't get it right.
Straight lines, and are completely inelastic. Nowadays, we know that most matter is actually composed of mainly void space. The space between the protons and the electrons is far greater than the size that they occupy.
Yeah, well, we can't be certain of any of that stuff, frankly. These are, again, tiny dots on the paper. We have these little Faraday experiments, or Rutherford experiments, and they're really not enough.
These ultramundane particles pass through most matter as if it did not exist. Now, this notion of an atom with mainly void would not be confirmed until the early 20th century. But the important point to note is as these particles
So a lot of these things they could confirm, like the polarization of light and the realization that a photon can't be produced by a single electron because the polarization is gigantic. And a tiny electron can't possibly be responsible for creating polarization that is so huge.
pass through the atoms, occasionally they may collide with the nucleus and be absorbed. Now this does not occur very often, but the more mass an object has, the greater the chance that this may occur.
So it's not that unlikely when you think about it, right? That the force is going to hit electrons and that every time it does, it's going to consume a little bit of energy. A little bit of the momentum of the force.
Now if you think this is a little too far-fetched, then I only need to bring your attention to the neutrino. This is a particle.
Alright, so why bring that up, right? In the context of Lesage and talking about a particle gravity theory, I mean this imaginary neutrino crap, that's just a theoretical thing. It's not a real thing. There's no neutrinos. It's just a silly invention. Neutrinos, if they exist, if there is some real thing that's filling the void of the neutrino, it's just a gamma ray or an X-ray. It's just some form of energy. It's not any kind of neutrino. It's not an individual particle, it's just a force. It's a broken photon. And broken just means we know that we can only receive photons that have a certain number of elements to them. And the frogs can see photons with fewer elements. Well, what if you go to fewer elements than a frog can see? That would be a neutrino. Okay, it's something moving the speed of light, but it has less elements than a usual ray of light, and therefore has a smaller mass.
Which, for the most...
But they all have to have a mass. You can't have momentum unless you have mass. I mean, it's just kind of silly to have a conversation about momentum without mass. But they do it.
part passes through all matter. The neutrinos are, however, too few in number to be our actual ultramundane particle.
I mean, again, the number of dots on the board for the neutrino is just so small. They just don't have good reason to assert these things exist with such confidence. There's just not a good reason. You can see the other camera. Yeah, production.
So how do these particles actually create gravity? To simplify this, we will consider this in only one dimension.
I do have this sped up.
Thank you so much for your patronage.
That crap is 2 ads for whatever dopey reason. Blah, blah, blah.
So imagine that there are ultramundane particles travelling in either direction from side to side. If we place a large body on one side of the screen and assume that some of these particles will be absorbed by the body.
So again, you could just do this with a theoretical thought experiment. Just say to people, look, you can understand this by just understanding something real, okay? A box and BBs. And you just understand the BBs never lose momentum. Okay, so they're just bouncing inside the box. You gave them momentum, they don't stop moving. They just bounce inside the box. And then somebody who knows some physics is going to be able to figure out, well, yeah, if I put an object in there that reflects the BB, that the objects will be moved right into each other. Because one object isn't going to see the BBs getting bounced off the other side of the other object, and there's going to be less pressure between them there. He's going to get hit less, and it's, facing the other BB. There's going to be less BBs coming at him.
You will see that part of the component moving from left to right will be missing to the right of the body, and vice versa. If we now introduce another body to the left of this one, it too will have the same effect. And it should now be clear that in between these two bodies, there are less ultramundane particles.
The shadow effect. But again, it's, you have to explain where the shadow comes from, and the fact is the shadow is cast in all directions. There's no need for the other object to exist. What goes in slows down, comes out fast again, but it used up some time, and by using up some time, there's less coming out than what's coming in.
Due to the absorption of some of them by either body. If we now consider that each time an ultramundane was absorbed, the kinetic energy of the impact was transferred to...
So again, the kinetic was transferred. If you do that, it won't work. So you can't transfer all of its energy. You're just transferring a tiny amount of its time. Sisyphus doesn't, just hit and run. Sisyphus pushes.
the body, it should become obvious that there is an inward force on both bodies causing them to move towards each other. So where in the standard view of gravity we see a pull force, here we see a pushing force from the sea of ultramundane particles.
I don't even know if you see a pulling force in the standard model. I mean, it's so silly. It doesn't have a force. That's the big problem. This stupid idea that space is bent in 3 dimensions. So it has a space vacuum cleaner. Every electron, every proton are consuming space. They're eating it somehow without ever pooing it.
To complete this picture, we must take this 1D view and add in the movement from all possible directions. And when this is done, what we will find is that this theory not only produces a force which is proportional to the mass, but also falls off with a square of distance between them. A critical aspect of this model, recognized by Lesage himself, was related to the nature of the collisions between the ultramundane particles and the matter itself. These collisions could not be entirely elastic, as this would lead to rebounds which would...
Right, so this was just the problem of conceptualizing the transfer of force. And again, in our world, we only understand things that are matter bits moving. That means they already contain a bunch of force inside of them, and that they exchange the force. This one has a bunch of force in it, moving in this direction. It transfers it to this one. So we see a world where force is transferred, and that's not what is happening on the elemental level. It's not transferring a force. It's combining the force with the matter, all right, and then releasing the force. So it's just using the force to move the matter. The matter hits, moves the thing. The force hits the matter, moves the matter, and then the force leaves. Obviously, it only leaves when something the other ways hits it, and so that's how you end up with a symmetry to the outcome.
Cancel out the pushing force. Instead, they would have to be wholly or partly inelastic. And if it was partly, then they would rebound with a reduced velocity. Lord Kelvin in 1873 became very interested in Lesage's theory. After he had published his kinetic theory of gases, he saw great parallels in how the two theories complemented each other. In his writings on this, he quickly determined that there would be a finite range of gravity beyond which its force would not be felt due to the noise of the background ultramundane particles.
Well, obviously the noise can't eat up the facts. So the fact is that no matter how much noise there is, you send one extra bullet, there's one extra bullet. It's just a fact. So, if I'm scattering bullets into the universe, the fact that they're very rare doesn't change the fact that they're there. And there'll always be 1,000,001, okay, for the one I added. So you can't ever make the force go away. As long as you have an infinite amount of time to play with, okay, it all has a symmetry. But yes, in realistic measures of time, something can be quite invisible for quite a long time. You won't know of its existence.
He determined that this range was proportional to the mean free path of the Lesage ultramundane particles, which would in turn determine their diameter and numerical density. At the time, Lord Kelvin estimated that if the particles were small enough, this range would be beyond our current visible limit. And this became an important...
So again, the trick is they're trying to figure out these mechanics when they really don't understand that there are these speed limits, that all the forces are doing all of the... They're creating all of the motion. Again, if you don't understand that, okay, that when something's moving, something real happened to it. Not a frame change, okay? It really has momentum. It's a real thing, momentum. It's a real thing, motion. Okay, it's not always just relative. It does exist in an absolute frame also. They're not incompatible. Okay, you can have relative. You can understand two things are moving the same way, and so obviously they have a similar precondition. But they actually have a motion through space that is consistent. They either are moving or they're not moving, and they're either moving this way or they're moving that way. They're not moving all ways. So I mean, you can understand there is a real physical mechanism. So if you understood that everything that's moving, okay, yes, it could be that you're moving, okay, and that it's stationary, and so it looks like it's coming right for you, but you don't know you're moving. But the truth is something's moving. So if something sees something moving, one of them is moving. It's really moving, and they both could be moving. Those are both legitimate answers. But the idea that neither is moving is silly. And that's relativity.
important concept, as with a finite gravity range, it would be possible to have a gravitationally stable universe, i.e. not contracting over time. Kelvin's main contribution to the...
So that's another one of these catches. But the point is this energy theory means that the more the matter is interacting, that is gravitationally or any other way, collecting, condensing, that the less energy there is in the outside universe. So that's sort of the catch. Let's see, it's a way to say that. So that the total amount of energy in the universe is dependent on how much interaction there is. And the less interaction there is, the more energy there is in the field. And the more interaction there is, that's going to decrease how much energy is in the universe. And so the gravitational constant could theoretically change as the universe consolidates. And then the gravity will get actually weaker, and then it'll fall apart.
Sage's work lies in the collisions. He argued that the elastic collisions might be feasible if, after rebound, the translational energies were given over to rotational or vibrational energies, conserving the total energy of the system.
Right, so it's just another way of saying that you have to equalize things. And the point is that, no, you have to understand that the energy is in the motion. The thing that gives the photon or the ultra-mundane particle momentum is its velocity, its movement in space. And it's not transferring its movements, it's sharing its movement. And by sharing it, it slows it down. It takes a little bit of its momentum away for the period of time it's moving it. So when that blue thing hits the yellow thing, all they have to do to this analogy to understand it is to have the blue thing stick. And now the yellow thing moves with the blue thing at a slower speed. And then the blue thing leaves. And that works. That explanation explains it. So...
The Sage's model had been criticized for requiring an endless expenditure of energy from the outside. It had also been shown that these rotational energies would later be restored via other collisions, keeping the ratio of the different types of translational energy.
See, if they did all this translational, rotational, then you would see a difference between photons regardless of frequency. We could create spinning photons, so we could create red light that's spinning left and blue light spinning right, or some other kind of stupid thing. There is no rotational energy. Photon is a photon is a photon is a photon. The elements of a photon are always the same. All you do is increase the number of quanta. There's no quanta plus. There's no quanta minus. It just doesn't exist.
Constant, and this eliminates the problem of gravity slowly being reduced as all the kinetic energies are converted to rotational energy, slowing the average movement of the particles down. Even the likes of...
There's no photon spin, so every time anybody ever talks about the spin of a photon, they're just talking silly talk. Just no evidence that you can have translational style added momentums. You can't do any of that. Can't slow a photon down, can't do any of that stuff. You can only impede its progress. You can't retard its velocity. You can only force it to carry something in the car, so to speak. The engine always runs at the same speed. You just put more weight in the engine, you're pulling a trailer, you're not pulling a trailer. That's the metaphor. When a bit of force is pushing an electron, it's like it's a car pulling a trailer. The car can only run the engine at one speed, so you're not going to go very fast when you're pulling a trailer.
And Maxwell were interested in this concept. In the end, Maxwell was the figure who put a nail in the coffin for this concept, for a considerable amount of time. He condemned the
He really didn't, and blah blah blah, and blah blah blah.
Theory based on thermodynamic grounds, stating that the temperature of bodies must tend to approach that at which the kinetic energy of the ultramundane corpuscles. Maxwell assumed that the kinetic energy of the corpuscles, the ultramundanes, was much larger and therefore ordinary matter should be incinerated within seconds under a Lesage bombardment.
Yeah, well, you can pervert anything by doing something it can't do. So if you force pigs to fly, you got all kinds of aerodynamic problems. And it's not going to work out very well. So yes, if you have the wrong assumptions, then you can defeat any theory with false notions of the reality, and that's all Maxwell did. And clearly can be understood if you understand this is ultramundane, and we do see that things are hot. There's lots of things that are hot, and there's no reason for them to be hot except for the tension created by gravity, except for the movement being created by gravity. The Earth as an example. The Earth isn't doing any conversions of helium into hydrogen, so why is the core melting? Well, it's because there's a lot of matter moving. That's why.
Preston, however, questioned Maxwell's assumption that the number of corpuscles was much smaller than the number of particles of ordinary matter. Preston demonstrated that if you assumed a large quantity of corpuscles,
the pressure of gravity is effectively being seen in the fact that the Earth's core is melted. That's gravity. Pressure is heat.
with a small mass. This would allow the Lesage gravity pressure to be maintained despite the low kinetic energy. As you can see, this theory has existed for a considerable amount of time, with equal supporters and opposers too.
No, equal. That's silly. It's nowhere even close. And unfortunately, yeah, it still exists as a piece of history. Okay, but clearly, 99.99% of all people doing thinking on the subject don't even know this exists as a theory, and this piece of history, and certainly haven't considered it as a possible answer, because it's not provided them. They're not provided the information that this was the road physics decided was no good, and it's such a good road. First, it has push in it, which makes so much more sense. And all you need to do is explain why more goes in than what comes out. And that's all you're trying to do. You're just trying to say, look, we know more pressure goes in than pressure that comes out. Why? Oh, we just slowed the light down a little bit.
So the main problems have hampered the development of the Lesage model, which can be summarized as follows. Number 1. If the collisions are partly inelastic, the transfer of energy would cause a heating effect. Depending on the mass and the velocity used, this could create a vast amount of energy that would build up over time. Secondly, planets which orbit...
So obviously the energy is quite efficient because it's moving electrons and protons, and we know they're jiggling. We already know this effect exists. We already know about Brownian motion, and that the Brownian motion goes all the way down in the sense that the nuclear bits are doing the same thing. And you're just accounting for the motion. You're saying, why is the matter moving? Well, that's because gravity's moving it. It's moving the subatomic particles all the time, and it's moving them in more than one direction. See, they think because something goes like this, there's no energy. No, there's a lot of energy, right? This is a lot of energy. So they already know the right answer here, that they have to account for all of that jiggling. Well, where's it coming from, and what energy is it consuming? Well, the very energy that is the push back. It can't push back because it's going both ways. It's undoing it, so it can't push back enough, and that's why there's gravity. It used up the energy. That's no other way to say it. It took some energy away from the universe to move the matter.
The sun have to move through these particles, and this could cause a drag effect, which we do not see.
Right, but we do see it. Electrons drag to a halt. Protons drag to a halt. We can't trap them in a magnetic field and just have them swirl around for days and days and days. They won't do it. Okay, you have to keep pushing them with more energy. You have to keep shooting more X-rays behind them, to keep them going. It's so obvious that's what's happening. All of the devices they use to move electrons and protons, guess what? They produce a ton of gamma and X-ray radiation. Every one of the devices that guns electrons or protons, those guns shoot a ton of X-rays and gamma rays. A clear, see how it all fits? Once you start getting the right answers, a whole bunch of everything else falls into place.
Both Kelvin and Lesage got around this problem by having the corpuscles travel at speeds much greater than the speed of light, and having almost negligible mass. However, when general and special relativity were introduced,
you still can't get out of it, okay? The drag argument is a solid argument about the fact that as you're moving into, you're going to hit more stuff in front of you than behind you. So it's always an argument. And the only way to get around it is to create something sophisticated, complicated. And that's why helium nucleuses, we can throw them into space. I can throw a helium nucleus to the moon and it'll get to the moon. If I throw an electron, it won't get there. Throw a proton, it won't get there. But a helium nucleus will. So a helium nucleus has a configuration that allows it to overcome drag. And that's the key. Matter can overcome drag. And it's based on the fact that nucleuses can change their shape and by changing their shape become pointy, so to speak, and get through the drag.
This was yet another nail in the coffin, as nothing could travel faster than the speed of light. Number 3. If we assume elastic collisions as Kelvin proposed, then this would lead to a build-up of corpuscles around the large body. The combined
Right, well that's because you consume their actual energy instead of using it for only a period of time. You're not transferring energy. So again, you just can't use this idea of transfer. I'm carrying a passenger, I give my passenger to the other vehicle. No, that's not what's happening. You have an engine, and you're forcing your engine to do extra work, and then your engine goes back to normal again, in the sense of normal amount of work. So it's just an argument that there's only a tiny period of time that your momentum is being used, and it's only during that period of time that it is being used. It's not a permanent change. It's only a transitional change from while you're pushing a piece of matter. But that's enough to change the momentum in the universe.
influence of these and the many negative assessments in conjunction with a general shift away from mechanical ether theories has led to the progressive loss of interest in the Lesage theory. So why have I included this concept if it is so flawed? Because this is not the end of the story for push gravity. There are many scientists, including Holt and Arp, who have come to adopt and modify Lesage's theory of push gravity. And that is what
I didn't see that, actually. I mean, I did watch a lot of Holt and Arp stuff and read, and I didn't see him talk too much about that. But anyway, we'll see.
why it is important to understand the basic concept that Lesage introduced and the noted limitations of this model.
So again, Lesage didn't introduce it. So this guy is talking like he's done some research and paid some attention, and it's really unfair to say Lesage introduced this. Fadio did, okay? He's the guy who talked to Newton. Yeah, come on, be fair.
Next few episodes, I want to explore some of these modified theories so that we can see how these limitations can be removed and how many interesting aspects of this theory could lead into several alternative theories not directly related to gravity.
So, and he's showing an image that has nothing to do with like a particle theory, of course. So again, it's just woo in the music and woo. You know, when here he's really saying no, it's clump, 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 clumpy. And, so it should have clump music and he should have clumpy images.
Such as planetary heat emissions, planetary growth, mass increase over time.
So all this kind of crap, mass increase, this sounds like expanding planet kind of woo. I mean, so, nutter, sorry. Probably just heading for nutter crap.
And cosmic background radiation, as well as explain some of the more gravity-related concepts such as galaxy rotation and gravitational shielding. And lastly, a massive thank you to all of my
well, gravities are just, the rotation of galaxies are explained by understanding maybe the galaxies are falling apart. They're not getting smaller. They're calculating the gravity as if the galaxy's in a steady state. Well, maybe it's not. And if the state is it's expanding, then it would make sense. Now, if it's contracting, it's not going to make any sense. But if it's expanding, is it going to make sense?
Patreon supporters and those people who have made donations via PayPal. It makes a huge difference.
Yes, it certainly does, and all that kind of crap. But you don't need to be so gratuitous. Yeah. If people are interested and they are motivated, you just give them the hint. Be nice if you donated now and then. You could say that maybe once in a while, but every video and blah blah blah. It's just kind of tacky, frankly. But whatever. I'm doing things different than them. Yeah, duh. So this should be a video, and it should be okay technically, and hopefully everything worked all right, and we don't have too big a mess anywhere. Yeah, it's not too big a mess there, not too big a mess there. I do like I should have an empty window so I can clean up and have a nice empty thing here, so I can just hide this. There we go. That's what we need. Force matter interaction. That's all there is. All the movement comes from the force. The matter gets pushed around, and that's all there is. Force pushing around matter. That takes care of interaction. That's all it is. That's all there are. If something happens, it happens because it was forced to happen by the force. And the force changes as the matter changes its position. The force changes where it's going. Does that make sense? Yeah. The force tells the matter where to go, and the matter tells the force where it's going to end up. And so that's the yin and yang, and you don't need any more. That's all there is. All right. So, till the next time and such, and so forth and whatnot. Yeah.